If you're still typing your coding prompts, you're leaving performance on the table. You're prompting cursor over 100 times a day, but type
size is still constant. Now, what we're going to learn an array of all characters that show up in all strings within this list. I feel like Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, find common characters. We're given a string, or basically a list of words. And so the way this is worded is honestly kind of confusing to me, but let's break it down. We're going to return an array of all characters that show up in all strings within this list. I feel like they probably could have used the word every, but that's just me. So what does that mean, and what does it mean when they say include duplicates? Well, the idea is basically just look at the example, don't even bother with the description half the time. These are the words we're given: Bella, label, and roller. Which characters are common to all three strings? It looks to me every single one of those words has an E in it, and every word has an L in it. But the result is not EL, it's ELL. And that's because every word actually has two L's in it. This has two L's, this has two L's, and this one has two L's. So this is the result. B is not common to all three. It's common to the first two, but not this one. R is not common to all three either. A is not common to all three, etc., etc. So that's the idea. Now, how do we solve this problem? Obviously, the fact that there are duplicates in here highly suggests the fact that for every given word, let's at least count the occurrences of every single character. So let's do Bella. Looks like we have a single B. Looks like we have a single E. We have two L's. I'm not really sure how to make this look not like a one, but and we have a single A. We can do that for the other two words. I'll just kind of fast forward that. So we counted the words. Now, let's just go through every single character. B, it looks like it's in these two words, but not this one. So we can't include that in the result. What about E? It does look like it's in all three strings, and it has a count of one. Suppose this one, for some reason, had two E's in it. What would we do? Well, we'd say this one has one E, this one has one E, this one has one E. It technically has two, but we have to take the minimum, right? We have to take the intersection of these three and then minimize it. So we'd say we can only have one E. In this case, though, this one already has one E anyway, so it makes our life easy. So we just put an E down here. Next, we look at L. It's in all three of these. So the count of it, again, is two. We take the minimum, and it's two in all of them, so we would take two. If suppose one of these only had one L, then we'd have to take the intersection. These have two L's, but this one only has a single one, so we'd have to put one L. But that's not the case. Each of them has two, so we can put two L's in the output. Last, A has a count of one in these two words, but it doesn't show up in this word. Now you might think, well, don't we also have to look at some of the other characters? Like, we only looked at B, E, L, A. We did not look at R, nor did we look at O. But my claim to you is we actually don't need to look at the keys of every single word, because we only care about the keys that show up in every single word anyway. So it doesn't matter whether we iterate over the keys in this word or we iterate over the keys in this one or this one. We just have to pick a single word and then check which of those keys belong to every single word. The answer will be the same. Like in this word, we see that E and L show up in the other words as well. R doesn't, O doesn't either. So now this solution does work. This is a perfectly valid solution. Just count the occurrences for every single word, then just pick one word arbitrarily, go through the keys of it, check does that key exist in all the other words, and then minimize the count. This works. It's kind of complicated to code up. And also, if you think about the space complexity, every single word will, like an individual word, will only have up to 26 distinct characters, lowercase a through Z, I think. But the number of hash maps we're going to create, each one of them is going to be constant size. That's what I'm getting at with this. But the number of hash maps we're going to have to create is going to be proportional to the number of words in the input. Let's say that's n. So the overall space complexity is going to be big O of n. We can actually reduce the space complexity to 1. And I'm going to show you how that is. We're going to take, let's say, one of the words, this one, and then we're going to build a hash map with it. So this is constant space so far. Once we have that hash map, we're going to say, okay, this is the most amount of characters that could possibly be in the output. Like, we can never have more than a single E in the output, because if this word doesn't have multiple E's, it doesn't matter how many E's the other words have, because we have to minimize the count. So, okay, so this is at most the number that we could have in the result. Now we're going to count a second word. Let's pick this one just to make it more interesting. So we have these two hash maps in memory. This is still constant space. Having two hash maps that are of constant size is still constant. Now, what we're going to say is find the intersection of just these two. Before, we were finding the intersection of all the hash maps at once, but now we're going to do it pairwise. We're just going to look at two hash maps at a time. And so I'm going to pick this one to iterate over. Let's check. B, is that common to both of them? No. So what I'm going to say is, screw this. B is never going to be in the output because we found at least one word that does not have B. Okay, let's try E. Okay, it does show up in both and the count is the same. So let's keep this. What about L? Shows up in both, count is the same. What about A? It does not show up in this one, so screw it. We only have these two left. This is the max that our result could possibly have. So we've gone through this word and we've gone through this word. Now let's look at this word. Throw it into a hash map and then start comparing. Let's check. Does E show up in both? Yep, and the counts are the same. Does L show up in both? Yep, the counts are the same. So now we've gone through every single word. This is no longer in memory. This is the result. But the only thing we have to do is take this hash map and convert it into a list of characters. I think you probably know how to do that. We're going to iterate over every single key. So we're going to have a loop for that. Let's say every single key in the hash map. And then in this loop itself, we're going to iterate for however many times, let's say I in the range of this quantity, this number. So in this case, it's 1. So we're going to add a single E to the output. And then we're going to iterate 2 times for L, and we're going to add 2 L's in the output, and that's the result. So space complexity, as you could tell, was constant. What about the time complexity? Well, in the worst case, we're pretty much iterating over every single word in the input. We're doing that to throw them into hash maps, and then we're potentially going through the unique keys. That's not going to be super expensive, though. This is the bottleneck. So overall time complexity is going to be, let's say n is the number of words. Let's say m is the size of the longest word or the average length of the word. It doesn't really matter. And this is going to be the overall time complexity in that case. The beautiful thing about Python is that we can actually take a given word and get the count of every single character very easily. We can call counter, let's say on the first word. We're guaranteed that there's going to be at least one word in this list, so we don't have to worry about index out of bounds. So this will return a hash map with the count of every single word. Great. Now we want to go through the rest of the words. What I could do is say I in range from 1 to the length of words, but actually this solution is going to work out the exact same even if we were to iterate over that first word once again, because when we take the intersection of the first word with itself, it's not going to change this hash map at all. That's why it works, and I prefer this because it's more concise, but it really doesn't matter. You can do it the other way if you want to save one iteration. Now I'm going to take the current word. I'm going to call this current count. I'm just going to call counter on that word as well. So now we have another hash map with a count of every character in that word. Next, I'm going to go through every character. I could actually pick either one. I could pick this one or this one. I'm going to choose this one just because this one is never going out of memory. Like this one is declared out there, and this one we're going to keep reassigning anyway. So I'm going to say for character in count. And I'm going to say, let's get the count of this character in this word, and let's get the count of this character in the other word. And I'm going to take those counts and try to minimize them, and then I'm going to reassign that back to this one. It's possible that maybe this character actually doesn't even exist in the other hash map. In that case, counter is kind of like a default dict. This will evaluate to 0. So in that case, This would end up being set to 0, basically telling us that we don't want any occurrences of this character in the output. So this is pretty much just to get the count of every character that we want in the output. That's what this portion of the code is doing. Now is the time to actually build the result, build that array that we're going to end up returning. So I'm going to go through every key now that's in this hash map. And I want specifically the count of this character. So I want to loop that many times. It could be 0. So we might end up looping 0 times. So I'm going to say for I in range, whatever this count is, it could be 0 or it could be a positive number. If it's a positive number, we want to add obviously this character this many times. We will just do a very simple operation, append to the list. I'm going to say for I in range, whatever this count is, it could be 0 or it could be a positive number. If it's a positive number, we want to add obviously this character this many times. We will just do a very simple operation, append to the list that particular character however many times we want to. It could be 0 or it could be more than that, and then return the result. It doesn't matter what order we add the characters in, so that's the good part. If it did, then maybe we could sort it or something. But now let's run it, and as you can see on the left, this works. Obviously the space or something, but now